Well, welcome everybody. My name is Ian Mosley and this is webinar number 9 of our Powerful Knowledge series. And today we're going to be talking all about magnetics design. And this is one of my particular areas of fascination, actually. It's an amazing area to get into. And hopefully I can convince you it's something you should get into as well by the end of today's webinar. As I say, this is the 9th of our series of Powerful Knowledge webinars. We're nearly halfway through. We've got a lot more interesting content to come. I know a lot of people have been asking for on-demand access for these webinars, and you can access them now on our website. If you need to know the link, let us know. All the previous 8 webinars are on-demand accessible, so hopefully there's some information there that's useful for you. On this webinar, we're going to be talking about magnetics design. Firstly, why do you want to design your own magnetics, and then going through some of the theory about how you can go about doing that. On the call today, I'm also pleased to be joined by Jose Gonzalez from Warwick University. He's an assistant professor, and he's been presenting the last few webinars all about advanced silicon carbide devices. Today, Jose is going to be manning the polls and questions side of the screen. So if you look on the right-hand side of your screen, you'll see 4 main areas. There's a chat box, so you can put anything in there you like. You can say hello to everybody if you wish to. It's publicly visible. There's a question box. So if you have technical questions as we go about the content of the webinar today, please do enter them into the question box, and we will spend about 15 minutes of the webinar, at the end of the webinar, to go through some of those. And I'm hoping we get some really interesting questions about magnetics design. There's also a polls box. So Jose will be launching some polls throughout this webinar to get a little bit more of an understanding on whether the content we're presenting is useful for you, your sort of the current understanding you have at the moment, really just to get us to have a more of a feeling about your, the relevance of what we're talking about today. This presentation will last about 1 hour, something like that. I hope there's quite a few slides to get through, so we might overrun a little bit. And I think I'll just get started now. So let me just share my screen. Bear with me a minute. Okay. Excellent. I think that's it. Yes, there we go. Right. So to give you an idea what we're going to talk about today, firstly, I'd like to describe why I think we might want to consider and when we should consider designing our own magnetics for power converters. I'll then go through the typical requirements that different magnetic power components have and the roles they play in a converter. There's going to be a section, a magnetics refresher section in this webinar, and to pre-warn you, there is going to be some equation. There are going to be some equations in there because some of these equations are fundamental to how magnetics work. I've tried to keep those at the highest level possible so that we do a good job on presenting the concepts as much as anything else, and really the equations are just underpinning those concepts and quantifying them. So there'll be a refresher section. We'll also talk about some of the loss mechanisms that you will need to deal with if you are designing your own magnetic components. There's a few images there. One of the problems most people seem to have with magnetics is how do you start? What is a suitable design framework? And I think the reason that this becomes problematic sometimes for folk is the fact that you can start your magnetics design from multiple different points of reference. There's all sorts of different ways you can design magnetics, and I want to present a design framework that we use here, which we found to be quite useful, which puts a methodology behind your magnetics design approach. And I'd be very interested to see whether that's something that you think makes sense to you as well. I want to give a case study of a 50-watt flyback converter transformer, where we've actually gone through used that design framework and actually gone through and wound that component and taken some measurements, just to show you how straightforward it can be to wind your own parts and how quick it can be. And then we'll finish up with summary and questions at the end. So, firstly, magnetics. Why would we want to design our own magnetics at all? It seems like a lot of effort if you can just go and buy them. Well, let's take a look at the comparison between an off-the-shelf piece of magnetics and our own custom designed piece of magnetics. So the good thing about off-the-shelf, firstly, is that it's quick to source and test. You can go and buy them from DigiKey or RS or Mauser or Farnell. And for simple converters, things like buck converters, often that works just fine. You can just buy the element, put it on your board, and it works. You don't pay NRE costs, brilliant. And the economies of scale means that the unit cost for an off-the-shelf part is generally about as low cost as it can get, because they're making millions of them. So that's all looking pretty good for just using an off-the-shelf part so far. However, these are where the downsides come. You nearly always compromise when you use an off-the-shelf part. You nearly always compromise on either the performance of your converter or the size, because you're using a part which is being made to be a generic part for multiple different applications. You can get away with it on simple converters, but as you move into more complex converters, it's less likely you're going to be able to get away with that level of compromise. And certainly when you start moving to high power systems, and one of the polls we're going to launch on today's webinar is a poll to understand what sort of power levels you're dealing with. As you start moving up in power levels here, and particularly when you start using or needing isolation in those magnetic components, it's unlikely you're going to find a suitable part off the shelf. They just won't have made exactly the right part you need. So let's compare that to custom magnetics. Now, by custom magnetics, what I mean by that is that you maintain the design authority for that part in-house, and you do the prototyping in-house. But what you should always do when you're doing that is to closely collaborate with your magnetics vendor, the person who's going to make this part for you. Try and collaborate with them from an early stage, because they're very, very good. The magnetics vendor is very, very good at telling you whether what you're trying to make is actually manufacturable or is going to be expensive, because you're trying to make it do something very particular in the process. So custom design doesn't mean you just lock yourself away from the magnetics vendor. You need to work closely with them, but you drive the actual physical design of that component with their support from a manufacturing perspective. Okay, the downsides then of custom magnetics, obviously it's the opposite of off the shelf. So these parts can be slow to source, and often you need to pay an NRE to the manufacturer. So that's a negative. The unit cost is going to be higher than off the shelf. However, the performance you can get can be fully optimized for your application. And that's the key part when you're running at high power levels. You really need to nail the performance so you don't have heat problems or reliability problems. One thing we found as well is that when you start designing your own magnetics, it actually helps you develop a deeper understanding of the power electronic system, because the piece of magnetics, the transformer, doesn't operate in isolation of the rest of the power converter. Things like your choice of switching frequency, control, all sorts of aspects of your design, like your switching frequency, for example, have interplay and bearing on the magnetics design, and that you need to be able to perform those compromises between those trade-offs between the magnetics design and the rest of the power converter. So if you can design the magnetics, you understand at a deeper level how to play those trade-offs. And actually, as I said before, for high power levels and with isolation, you probably don't have an option. If you really want to have a good design, you have to design your own parts. So what I'm focusing on, and really, are those three key points from a custom design. You can't get them off the shelf, and especially when you're pushing to high power levels and high performance, you really need to take ownership of driving that magnetics design yourself, and that's really what this whole webinar is going to be about. The one thing you can do, or the one negative of custom parts, is they're slow to source, and this NRE can be expensive. We get around that by winding our own first prototypes in-house wherever possible, because you can do that quickly. You can iterate quickly, and obviously the NRE cost and actually it's more the time delay. If you're waiting 2 months for a sample to come back from a magnetics vendor and it's wrong, that just messes up your project schedule completely. So you need to be able to really do this stuff in-house. So that's how we iterate fast, and we get to a design that works really well as quickly as possible. So hopefully that answers the question on why you might want to consider building your own magnetics. In terms of typical requirements, okay, there's a number of key functions that magnetics components play in a circuit. So let's list those out. So firstly, transformers provide galvanic isolation between parts of the circuit, which is essential for many different applications. You can implement turns ratios on those magnetics components. So if you're trying to step down a very high voltage to a low voltage, or conversely go from low voltage up to high voltage, then you need a turns ratio to make your duty cycles in your converter sensible. The components can store magnetic energy as well. Now, for some converters, that's actually a key part of how they operate, and certainly for an inductor is an energy storage element, so that's a key function of that part. Firstly, let's have a look at transformers. So transformers obviously provide galvanic isolation. That's one of their first key attributes. Inductors don't do that. They're just an energy storage device. Transformers can implement a turns ratio from primary to secondary, or multiple outputs if you want. Inductors don't do that. They're just, again, a single turn winding, often just there to store magnetic energy. Now, a transformer, in terms of energy storage, is a tick and a cross. And whilst all transformers will store some energy, what I mean by the tick and the cross there is that in some applications, some specific topologies, you're actually your design of your transformer utilizes that energy. And the flyback converter example I'll give later on in this presentation is an example where the energy storage in the magnetic field is a key attribute of how that flyback converter works. Some topologies don't require that energy storage in the transformer itself. The inductor, though, finally we get a tick for the inductor. The inductor's function is magnetic energy storage. That's what it's there for. Okay, there are some other requirements here. If you're using a magnetic core, we'll see later on from the material properties that the core can saturate. And when the core saturates, basically it looks like air. So we mustn't saturate the core, otherwise our inductance drops through the floor and everything goes wrong very quickly. If you've got a turns ratio and galvanic isolation between two different parts of the circuit, often you have to meet creepage and clearance requirements, which are dictated in the safety standards. So you have to think about spacing and insulation and all that sort of stuff. And you've got to manage power losses. So in this webinar, I'm also going to describe some of the main loss mechanisms that you'll experience in magnetic components and how you can design and quantify those. Other parasitics come in as well. Whenever you've got physical windings, you can have leakage inductances and capacitance between windings, and there are different techniques to help you trade off those parameters as well. Low capacitance is normally a good thing for high switching frequency. So I've warned you about the magnetics refresher. Hopefully this isn't going to be too in depth on the mathematics side of things. Please, if you get put off by the maths, please bear with me, because what I want to do ultimately is to run through this maths fairly quickly to just show the key outputs of this, which we can then use as a sort of figure of merit approach for designing the magnetics component. But it's useful to have this background as a starting point. Firstly, now, if you remember back to the early days of your studies, you'll probably remember Faraday's law. So if you have a winding with n turns and you put a fixed voltage across it, you'll have a linearly increasing flux. So V is n d phi by dt, standard sort of Faraday's law. And actually, if you look at the flux, you see that the flux there, phi, is directly proportional to the current flowing in the winding. So you could just have that winding just without a core at all. And in that case, you have an air-cored coil, which I've shown a finite element model of one of those air cores here. Now this here, we've got 31 turns carrying 2 amps with about 10 millimeters diameter for those coils. And it generates a field pattern that looks like that. The actual absolute magnitude of the field is not important. But the one thing that is important is with an air-cored coil, to take a look, if you were to draw a horizontal line through that plot and measure the flux density, so the flux density is the flux per unit area, what you would see is something like this. And this is an output from the FEA system as well. You can see within the coil, confines of the coil, we've got a fairly constant-ish sort of a flux density, but outside the coil, you can see we've still got a fairly high non-zero flux density level. So with an air-cooled coil, it's quite difficult to control where the flux lines actually go, and that's a problem because the flux lines, if you're creating a transformer, need to link between different windings. This would create a very leaky transformer if we were to try and build this. So what happens if we put a magnetic core in the circuit. So we've got the same coil in the middle now, and we've put an E core around that, in this case with an air gap as well. So what happens is that the permeability of the ferrite material here is very high, and with a high permeability material, what happens is the flux finds it much easier, wants to flow within that high permeability material. So what the magnetic core does is it allows us to control where the flux actually flows. We get a little bit of fringing around the air gap, but you can see here the majority of the flux generated by that same 31 turn coil with 2 amps flowing in it is pretty much concentrated all within the ferrite core here. And if I take that section through again from left to right showing flux density, you can see here now we've got far more controlled flux density. So this is the center leg. There's a little bit of fringing because I've taken this section where the air gap is. There's a bit of fringing where the air gap is. In the outer legs, so this is an E core, so the flux goes up the middle and then comes back down the 2 sides. So again, we've got some flux density on the 2 outer legs, which is nice and square. So the focus of the core here really is just to control where the flux flows and to focus it into the areas we want. Now, if we were to put a second winding on top of that first winding, then the majority of the flux that is essentially flowing and linking the first winding will link to the second winding, and that's when we get a transformer action. So if that changing flux links to that second winding, we induce a voltage and we have a transformer. Now, not all of the flux generated by the first winding will link to the second one, and that flux that doesn't link to the 2, that's actually our leakage inductance, and we'll talk about that a little bit more later on. Okay, now the key thing here is we've got energy stored in that magnetic field, and the winding therefore also has inductance. And I'd like to quantify some of those concepts now as well. So moving on, we're going to move into a little bit more of the maths now. So stay with me on this. So we've already spoken about Faraday's law, V is N d phi by dt. Now, if you look at the equivalent sort of inductor equations, you get V is L di by dt, just standard stuff. So therefore, we can compare those 2 equations directly, and we get this equality, N phi is equal to L times I. That doesn't seem that useful at the moment, so let's move on. We can also say that the phi flux is equal to the flux density times the cross-sectional area through which the flux is flowing. So phi is equal to B times air core. We can call it air core maybe. And the inductance L is equal to N squared upon S. Now, N is a number of turns on the coil, and S is actually something called the total magnetic reluctance. And a good way to think about reluctance is it's a bit like the magnetic world equivalent of resistance. So if you have a high reluctance coil, you need a lot of turns to generate the same amount of flux. So S is our total magnetic reluctance. Now, manipulating those equations here, let's just go through it. This is the key equation we get, and so this one in yellow, you can pretty much forget everything else. This is a key equation because you can see from this equation here that the flux density B is directly proportional to the current, as we mentioned before, and we can use this equation when we're designing magnetic components, and you'll see in a few slides' time how we use this to start equating the energy storage requirements for a component. So this equation in yellow, just keep that one in mind for the moment, and you'll see why it's useful later on. Okay, so let's take a look at an inductor. So we've got N turns on a magnetic core, and then the magnetic core has got an air gap, and we've got a total inductance L from those N turns. So you can also say, just a standard electrical equation, that the energy stored in an inductor is a half Li squared. Standard sort of definition here. And we know that L is equal to N squared upon S. And from the previous slide, remember that equation in yellow, we can rearrange that to make I the subject here. So I is given by that equation there. Now, if we combine all of that together, you can see that the energy stored in the magnetic circuit is just a half S and then product of B times area of the core squared. Now, that doesn't look that useful at the moment, but let's take a few more steps through this. What does S really mean? Well, the total reluctance S here is the total reluctance of the magnetic circuit. And remember, it's a bit like a resistance. So the total reluctance is the reluctance of the core plus the reluctance of the air gap. Now, if your core is very, very high permeability, like a μr of 1,000 or 2,000, something like that, actually the reluctance of the core is tiny in comparison to the gap. So the gap reluctance, S gap, is very, very much greater than the core reluctance. And therefore, the total reluctance of that magnetic circuit, you can approximate as being the total reluctance of just the air gap itself. And that might be a very small gap, but it dominates the magnetic behavior. And the definition of the gap reluctance, it's the length of the gap, so the length across here, you can see where my pointer is, divided by mu naught. So mu naught is 4 pi times 10 to the minus 7, and AC is the area of the gap. And for a first approximation, just assume it's the area of the ferrite here. So let's put those values into our energy equation. So again, a little bit more arithmetic and juggling here. You can see that the energy is equal to a half L gap AC divided by mu naught times B squared. Now that is a really interesting equation, believe it or not. And there's a few key things to note here. Firstly, and this is the really, really interesting part, is that the energy itself is actually stored in the volume of the air gap. You can see this L gap AC product is just the volume of the air gap. So if you make the air gap have more volume, either by making it longer or have more area, your energy storage goes up for a given flux density. So that's a really key point. The core here is just focusing the flux into that air gap, but it's the air gap that's storing the energy. The energy itself is proportional to B squared. As most energy equations are, there's always a square term. In this case, it's the flux density squared. And as I said before, the core is focusing the flux into that air gap. That's its job. However, now that we've got a magnetic material here, we can't go higher than the saturation of the particular core material, because then what would happen is the core would effectively disappear and would have a huge air gap. So we can't take Bmax higher than whatever the properties of the material are here. And it might be a few hundred milliteslas for ferrite. It might be more for iron powder. But this is a really important equation, because it shows you if you've got a design whereby you need to store a certain amount of energy in your magnetic component, this gives you a way to go about doing that. Okay, so this may have prompted a few thoughts. If the energy itself is stored in the air gap, which it is, it would seem that it's the best way to store energy then, in terms of energy density, is in air. So why bother at all with a core for an inductor? Why not just make it an air-cooled inductor? Then you've got a huge air gap and the possibility to store a huge amount of energy. Well, you could do that, but let's take a look at what that would mean in practice. So remember, L is equal to n squared upon S. And the total of the total S here is the sum of the air gap reluctance and the core reluctance. Now, if we were to take the core out of this system here, firstly, mu r is typically 1,000 to 2,000 for ferrite. So we can see that the impact of the core, when you have a small air gap, the core doesn't really contribute to the reluctance of the magnetic circuit. But let's take the core away. So let's remove the core, just turn those 31 turns into an air-gapped system. Well, what happens then is that the length of the air gap, or the effective length of the air gap, increases from that tiny level, which might be 0.2, 0.3 of a millimeter, and suddenly it's huge. So all of a sudden, our total reluctance increases massively if we go for a pure air-gapped approach. Now, if you've got a very, very big reluctance here, to achieve the same inductance level, you have to start putting on a huge number of turns. So the trade-off here is that the longer and longer and longer you start making your air gap to store more energy, the more and more turns you need to put onto your magnetic component to get your inductance that you need. And in the limiting case there, where you have a completely air-cooled inductor, you would need to put a huge number of turns on there, and you end up then pushing a load of loss into the windings. So really, an air-gapped approach with a magnetic core is a way to balance out the number of turns and the loss associated with the core material. And hopefully I've explained that in a clear enough manner. If we can always discuss that a little bit more in the questions section at the end. Hopefully that's been a good justification of why we want to use a magnetic core with an air gap here. So using the gapped core, it allows us to focus the magnetic flux into exactly the right places to store the energy where we want to. We can operate that design with a reasonable number of turns. And we can create windings which have a tight coupling to one another, because remember, we can focus the flux to where we want it to be. So it allows you to get to low leakage inductances as well. So they're the sort of the fundamental reasons of why we want to use a core in our magnetic component. What I showed you a few slides ago was what you would typically find with a ferrite core with an air gap. And that's typically used in flyback converters or high frequency converters, because ferrite is a very low loss material. However, there are other magnetic materials you can use and are very commonly used in switch mode power supplies. And one of the ones I wanted to briefly describe here are powder cores. Now, in these powder cores, you can get them in all sorts of shapes. Often they're used in toroid shapes like this, where there's no air gap. These are formed from a pressed iron powder material with a binding agent to hold them together. They give you something called a distributed air gap. So these imagine that the material inside that toroid is like a lot of iron powder material, and between each little iron powder element, if you like, there's a small air gap to the next one. So you end up with this distributed air gap all the way through the material. So it's a bit like having a ferrite core transformer with multiple tiny air gaps all the way around. And that's how they work. So you don't need a discrete air gap. It's sort of built into the material here. The other thing that's great about these materials compared to ferrite is you can get much higher saturation flux densities than you can with ferrite. So ferrite might be, I don't know, 400 millitesla, something like that would be a typical top end of where you would go to. You'd never normally design them that high. With these particular iron powder cores, you can push to 1 Tesla, beyond 1 Tesla as well. So you can store a lot of energy in them. And they also can operate at much higher temperatures. There's this Curie temperature. All magnetics have a Curie temperature. And that Curie temperature is the point at which, if you go higher than that temperature, the magnetic properties of that material are lost. So for ferrite, that's around about 200 degrees C. But you can see, I think I've highlighted in a minute, you can see that the Curie temperature for these iron powder materials is maybe 500 degrees C or 700 degrees C. It's much higher. So these are quite good for high temperature applications. However, there's always a trade-off. They look great on paper and they're brilliant parts. However, they exhibit far higher core loss than ferrite for the same operating frequency and flux density. So you've got to be careful how you use them. Where they're typically used is for output inductors in like a forward derived topology, like a buck converter or a forward converter, or maybe a phase shifted full bridge. In those applications, the output inductor has a pretty high DC level with a small ripple current on top. So what you end up doing is you can exploit the high saturation flux density capability of the material in that application with just having a small loss due to the small ripple on top. And I'll describe that in a minute on the next slide, I think it is. We've used these for high temperature applications, oil and gas, that sort of stuff, where you need your power converter to run well at about 170, 180 degrees C, where ferrite is starting to get too close to its Curie temperature as well. But that's quite a niche specialist area. Right, loss mechanisms. Hopefully you're staying with me on this. Let's take a little bit of a look at what causes loss in magnetic components. So firstly, for the magnetics material itself, that core, you can get something called eddy current and hysteresis loss. And this is just an image I took from a paper to try and help illustrate that. So with a magnetic material, what you're doing as you exercise up the flux density up and down is you're moving around this BH curve, which is a nonlinear curve. So in the first, you can see in the first plot A here, as we increase the MMF, we're starting to move round this curve on the bottom trace. And as we come back, we follow the top trace. and you can see that there's an energy lost. It's actually this energy in that's contained within the curve here. And if you're going bipolar flux, that would obviously happen the other direction as well. So that's hysteresis loss, and it's just a result of moving around that BH curve at high frequency. You also get eddy current loss. The core itself, the ferrite material, is electrically conductive, and that causes, when you've got magnetic fields being generated in the region of an electrically conductive material, it sets up eddy current losses within that material, which just cause heating. So that's another loss mechanism. What you tend to get is, for a particular material type, you'll have these loss curves where on the left-hand side, the y-axis here, a thing called specific core loss, or PV, and that gives you a metric in terms of kilowatts per meter cubed is a typical metric here. So for a particular size of component, you can work out loss based on the operating frequency. So operating frequency is on the x-axis. And then you get a set of curves which give you flux density. You have to be a little bit careful about how different manufacturers treat that flux density. Some of them treat it as peak, some treat it as RMS. So you've got to read through the details there. And you can see here that the curves vary also with temperature. So it's quite a complex thing to model, but we can use something called the Steinmetz equation to model that. And you can just analytically, you can work out, assume these are straight lines, you can work out these factors K, alpha, and beta. So F is your switching frequency, B is your peak flux density or RMS flux density, depending on manufacturer. So you can use this equation to compare different material types and get a feeling on the specific core loss. What I thought would be useful to do is to do a comparison of a number of different ferrite grades. So remember, ferrite is the material we're putting a discrete air gap into, and iron powder. So the iron powder, I took two different types from Magnetics Inc. here, because what I wanted to do is, for the same operating conditions, show the difference in specific core loss, to show why you might want to use ferrite or where you might want to use iron powder material. First thing to note, as I mentioned before, iron powder materials offer a much higher saturation flux density compared to ferrite. So the data here is taken from the actual data sheet from TDK here. So I would never run these flux densities. I typically run about 300 to 350 milliteslas max. But you can see here, as you move into iron powder, you can get to 1 Tesla, 1.6 Tesla. So you can get to much higher flux density levels. If we look at the Curie temperature, again, with ferrite materials, it's around about 200 degrees C, something like that. As we move into iron powder materials, depends on the material type, but 500 degrees C is commonplace. 700 degrees C is also feasible as well. So on paper, again, it just looks like iron powder material is way better. I worked out for the Steinmetz equation what the values of K, alpha, and beta would be, and made sure I normalized the B peak versus B RMS to make sure it's a true like-for-like comparison, and then plotted out for 100 milliteslas RMS AC flux density what the specific core loss for those materials would be as a function of frequency. And this is going from 10 kilohertz up to 500 kilohertz max. Now, it's a bit difficult to see on the plot here. So firstly, if I put some arrows on, you can see the lowest loss. So a low figure here would give you the lowest core losses. Ferrite is by far the lowest specific core loss for a given operating point. As I then move into the iron powder materials, cool mu is the next highest, but you can see here we're at cool mu for the same operating point is probably at least an order of magnitude higher specific core loss than ferrite. So you just couldn't run the same peak flux densities as you could do with ferrite and still have sensible losses. And as you go up to the X flux material, here, this is the one that you can run at 1.6 millitesla. If I go and take a look at that, you can see that the price we're paying for operating potentially up to 1.6 millitesla is incredibly high core loss. So what this is really saying is that you can use these these iron powder materials in situations where you have that high DC flux density level or high DC current with a small ripple on top. But what you absolutely can't do with iron powder materials is have a fairly high delta B. You know, you couldn't run from 0 to 1.6 Teslas at 100 kilohertz because the core would literally be on fire if you were using iron powder. So each of these materials has its own place to play. As you develop higher power systems running at higher frequency, anytime you've got a fairly high AC content compared to DC, be very careful of using any sort of powder material. Ferrite is normally the best for handling higher delta Bs. You just can't get the loss performance with the iron powder materials. So ferrite is great for a low specific core loss, but it has limited BSAT. Iron powder, again, is a trade-off with higher BSAT, but much higher specific core loss. And again, use that iron powder material for output inductors with high DC currents. Okay, briefly through skin effect. So skin effect is if you've got a DC current flowing through a winding, it'll flow uniformly within that whole, the whole cross section of that winding. As you start going up in frequency, you get an effect whereby the current wants to flow around the edge of the winding. And the skin depth is defined as the depth when the current density falls by 1 upon E. So as you imagine going into the depth of the conductor here, when the current density falls by 1 over E, that distance that you get is defined as skin depth. And there's an equation here that defines what that is. And in copper, I think I've worked it out. Yeah, so in copper, you can work that out and you get this expression, this curve here, where you can plot in copper skin depth as a function of frequency. And at 100 kilohertz, I'm using 100 kilohertz because that's a common operating frequency for many converters. The skin depth in copper is about 0.21 millimeters. So there's no point in using a conductor with a diameter greater than 0.42 millimeters if we have 100 kilohertz current, because you won't be utilizing the center of that conductor, and you get around that problem by using multiple individual strands or Litz wire. There's a couple of other loss mechanisms though that are sometimes less commonly known about. So most people know about skin effect. However, there's also proximity loss and fringing loss. So proximity loss, that's what happens if you've got two conductors side by side carrying current in the same direction. Those currents, that current flow will try to repel one another. So they'll flow in the outside perimeter of those two conductors. And if you've got current with one current going that way and one current going the other way, they'll try and attract. So they'll flow on the inside of the conductor periphery there. And in both cases there, you can see what's actually happening is we're not utilizing the full conductor cross-sectional area. It's essentially like an impedance or a resistance increase because we're just not being able to utilize the copper. And you can imagine as you go up in layers of windings, so you've got a 2-layer transformer winding where you've gone across and back, when you've got lots of conductors side by side, and your AC resistances start to increase significantly. Now you can model those with something called Dowell's curves. They're quite Dowell's equations and Dowell's curves. There's quite complicated maths behind it. The best thing to do is to look at the actual curves themselves. I haven't shown them here. It's worth taking a look at that if you're particularly interested in high frequency operation and how you can minimize winding loss. Take a look at Dowell's curves because they tell you a lot about how to model these sorts of an effect. And probably the one that's least commonly talked about is fringing loss, and this is a zoom in of an FEA analysis of a flyback transformer with an air gap in the center leg. So we've got the center leg here in pink with the flux flowing down, and then in the periphery of the air gap you can see we're starting to get fringing fields, magnetic fields that are moving out in towards the first layer of the transformer winding. Now remember, eddy current losses, if you've got a changing magnetic field and a conductive element, that will induce eddy current losses. So what happens is those fringing fields, they start generating eddy current losses in that layer of windings and cause additional heating. And I remember seeing this years ago with an inductor we'd designed, that the air gap was too big and it was getting too hot. We put it underneath a thermal camera, And you could see, it was amazing, you could see this strip of heat on the winding just above where the air gap was. You knew exactly where the air gap was because this particular strip of heat showed it very, very clearly. So fringing losses, if you've got a large air gap trying to store a lot of energy, the fringing loss can absolutely kill the performance of your converter. So you've got to be very careful with large air gap lengths because they can cause a lot of problems. So it causes eddy current losses in the wires near the gap. It's actually quite difficult to model. We haven't really modeled it specifically here. We use FEA to try and get a feeling on how to quantify it. I've read about various different rules of thumb, one of which I've heard is if you can keep your first layer of windings more than a distance of more than 3 air gaps away from the air gap, that will minimize the effects. Now, that's probably just another rule of thumb that you can play around with, but it's a good starting point that gives you an idea. For example, if you try and put a 1 centimeter air gap in your core, you want to keep your windings well away from that 3 centimeters at least, for example. So it gives you a bit of a sanity check on whether what you're putting together is sensible or not. Okay, what you can do is, rather than having one single gap, is you can make multiple gaps. So you can end up putting something, a design together, which is called a distributed air gap. So maybe in that center leg, rather than having one single gap in the middle, you could split that into 3 and have little segments of ferrite between them. And that can massively reduce the impact of fringing loss. It can be a very good thing to do. Okay, design framework. Okay, so again, as I mentioned at the start, there's multiple ways you can go about designing magnetic components. And I want to give you a design approach that we've used for designing an inductor, because this can be translated into other components as well. So let's take a typical ferrite cord inductor, whereby we've got, this is an ETD part, but it could be any platform. If we take a look here, we've got a core area here, let's call it AC, which is the area of the center leg. And we've got an available winding window area, AW. Now let's make our figure of merit called AP, or area product, the product of the AC value and the AW value, because that gives us an idea on a metric which captures the amount of space we've got for a winding and the sort of the magnetic capability of the core, or the core area. So let's work through what that means if we take this approach. So there's a bit more maths coming now. Hopefully you're still with me on this. Now, remember our equation from earlier. The area of the core, we can rearrange. Remember that equation in the yellow box? I told you it would be a useful equation. I'm going to use it again here. The core area AC can be written as this. Now, imagine we've got N turns here in our winding, each carrying a current of I RMS. AW is our winding window, and PF, let's call that our packing factor, because we can't necessarily make maximum use of that whole winding area for copper, because we've got insulation in there, we've got, they're round windings, you can't utilize every last bit of area available, so we have to introduce this packing factor. So the current density J, that's something that's useful to know, because that's if you drive very high current densities, you're going to generate loss. So we've got 2 equations here, and if we rearrange those using those 2 equations, we can work out that our area product is given by this expression here. Now, it doesn't look particularly useful at the moment, but the first thing to note is this. I think I've actually put it in. Yes, I put it in a note here, that the last component here, N squared upon S, that's actually equal to our inductance L. And depending on your inductor, let's say, for example, we've got an inductor that's supporting a nice high DC level with a small amount of ripple on top of it. Now, if we take that assumption for this particular example, we could say that the RMS current is roughly equal to the peak current in that case, because there's just a high DC level. Now, if we take that leap of faith and take that assumption, you can see that this equation then boils down into this equation. Stay with me. But I peak squared L is actually 2 times the energy storage here. So again, a bit of arithmetic here. We get another yellow box equation. So yellow box equations are the things I want you to remember. We get this AP value, this AC times AW, is equal to 2E divided by B peak times J times power factor. Now, what's great about that equation is if for your inductor, from the design of your topology, you know what the maximum energy storage is, which you should do, because that's part of your early stage design. If you know what the energy is, then you know what peak flux density you're happy to run at, because that's dictated by maybe the magnetic material you're using, maybe 300 millitesla. J might be is the current density you're happy to run the windings at. So for example, in copper, it might be about 3 amps per millimeter squared. If you run more aggressively than that, you'll run more heat in the windings. So that gives you, and you can see here, if you are happy to run with a higher current density, J is bigger, that means this core area product is smaller. So if you're happy to run high current density, you can get away with a smaller core. Or if you can run higher peak flux density, you can get away with a smaller core. If you can run a higher packing factor, so pack the windings more efficiently, you can get away with a smaller core. The key thing here is, with the assumptions of B peak, J, and packing factor, if you know what your energy is, you can actually then just come up with this ACAW product, which you can then use to look at normal cores that are available, and you can therefore work out roughly what the core size you'll need will be just by inspection. So I'm going to do the last part of this webinar is talking about how to use that methodology actually with a 50-watt mains flyback converter. So let's take a look. Now, before I dive into the details here, the reason I've chosen a mains flyback is a mains flyback is, people do call them a transformer, but technically they're actually utilizing the energy storage on the primary side as part. They're really a coupled inductor, although just call them a transformer. That's probably the easiest way to think of them. But we have to specify as part of the design process the energy stored in the core. It's a key metric for how the flyback converter works. Now, the first step of this is obviously to translate the target specification of this converter through to a requirement for the transformer. I'm not going to show that here, because that's not really what this webinar is about. This webinar is about taking the magnetics requirements and turning that into something you can make on the bench. So there's a leap of faith involved here, a bit of mental arithmetic, which will end up taking that spec and giving a transformer requirement of the following. So for those particular set of requirements, we want about 1 millihenry of primary inductance. That's a design requirement for the way the flyback works. We want a 2.77 to 1 turns ratio. Again, I'm not going to justify that here. Just believe me, that's what we want for this particular design. A bit of a leap of faith, I know. The peak primary current is just over 1 amp. And the peak-to-peak primary ripple current is 0.93 amps. So this one's actually running just into continuous conduction mode. So we've got some nice metrics there. And the maximum primary RMS current is 0.41 amps. The question is how do we then get a core size? How do we know what core size we need? Well, why can't we use that approach we used for the inductor, the area product approach? Remember, the inductor core area product approach is given by the equation you can see here, but we've not got an inductor, we've actually got a flyback converter. So what I've done, and it's not completely accurate, what I'm saying is that let's assume that the primary winding occupies 50% of the winding space. And if we were to do that, then what we can say is that you can just adjust that core area product equation accordingly. And for a flyback, therefore, it's just given by this equation here. So we can work out what core area product we want based on that energy storage. Now, for our design, remember from these output here, we need 1 millihenry primary inductance, and the peak primary current is 1.07 amps. And actually, for this case here, if you can just work out a half Li squared based on those two figures, that means that the transformer magnetizing inductance is required to store 572 microjoules. So it's a tiny amount of energy, but we can work out what it is. And that's our E figure to put in this equation here. And let's assume a starting point of current density of 3 amps per millimeter squared, a packing factor of 50%, which may be actually a bit optimistic, but let's say 50%. And let's say we want to keep to a peak core flux density of 300 milliteslas at maximum current. That then gives us, and if you use this equation here, an AC-AW product of just over 5,000 millimeters to the 4. Now, it's to the 4 here because you've got the multiplication of two areas. Let's take a look. What I've done here in a spreadsheet is to quantify, moving from left to right, various different core sizes and core types. So you might not be able to read that too well, but for each of those core types, I've noted down from the data sheets the cross-sectional area of the core in millimeters squared, and the winding area window, or the winding window area in millimeters squared, and multiplied them together to give us our core area product. And what we see firstly is that an EF30 core has an AC-AW product of 5,400 millimeters to the 4, which is therefore about what we need for this particular application. So great, you can go in here and you can see here that's about right. The winding current density is 3 amps per millimeter squared. I think this is that's energy, 0.61 microjoules, 0.61 millijoules. If we then look at the rest of the output from this table here, for the same point here, we need an air gap of 0.28 millimeters. And in terms of number of turns, we can read off again 61 turns on the primary, and with the turns ratio that I've shown you in the previous slide, we need about 22 secondary turns. Okay, so that's really just applying that core area product approach. Let's try making it based on this EF30 platform. So we've got an EF30/15/7 with 61 primary turns, 22 secondary turns, and 0.28 millimeter air gap. What we will also do is we're going to use something called a split primary winding to reduce leakage inductance, and I'll show that on this slide in a minute what that means. The winding width we've got is 17.5 millimeters, and we want our primary to essentially be 2 layers, so across and back. So with 2 primary layers, we can use an outer diameter wire for the primary of about 0.45 millimeters. And that, if you work out, gives you around about 2.6 amps per millimeter squared based on the primary winding RMS currents. That's about right. The skin depth at 100 kilohertz, remember that slide I showed you back at the start of this presentation, is about 0.2 millimeters. So 0.45 millimeters primary is about right. It's about what we want. The key thing actually is to make sure that that primary winding fits a full layer, because then you get a nice flat winding for the layers above. So sometimes you adjust the thickness of the diameter of the primary winding just to make sure you get a nice integer number of layers. On the secondary side, this is a mains converter, so we have to think about creepage and clearance. On the secondary side, I've actually used something called Texi wire. So this is the typical wire that you might use for the primary. It's standard enameled copper wire. On the secondary side, we're going to use this sort of wire, which is called Texi wire, and it's triple insulated, so there's 3 layers of insulation there. So you don't need to use insulation tape or anything like that, or margin tape. You can just get away with this standard wire. So we're going to use 2 parallel strands of 0.4 millimeter Texi wire, and that gives us a slightly higher current density in the secondary, but it's still okay. We still have the same issues around skin depth, so we can't use wire that's really thicker than that. It's a bit pointless to do that. Now this shows you the stack up and what I meant by an interleaved primary winding. So what we've got is you first wind half of the primary here is 1 layer. Then we wind our 2 layers back to back of the secondary using the Texi wire, and then on top of that we use half the primary. Now that has benefits in terms of leakage inductance, and we don't have time to really go into that on the call today, but that approach, that interleaving approach, allows you to minimize the leakage inductance in your particular design, which is an important parameter for a flyback converter. Okay, so I actually let's move on from all this theory and actually build this thing. So I had an EF30 core in the lab. You can see here, this is before I started winding it. So the first thing we do is we wind 30 layers of the primary in a single layer, just going across. Then I put some tape on, a layer of tape, just not for insulation purposes, actually just to mechanically hold the winding in place. Then I can bring that wire that was on the right-hand side, I can bring that back across and terminate it on a pin on the primary side again, and put tape over to hold it in place. The next thing I'm going to do is to wind the Texi wire. Now that looks a little bit more messy, but I've done my best job I can here. 22 bifilar turns across 2 layers. So we've started on the secondary side, we've come back across and then back, and then terminated here on the secondary side of the transformer. And the next picture actually shows quite a few things in one. So what I then did was to apply tape to that layer of Texi wire to make a nice flat layer to wind my second layer of primary on. So then I wound around the second layer of primary, starting from that middle point, going across the transformer, then put a winding of tape in place to hold it, and then bring the end winding back. We then need to adjust the gap for the required inductance. So the indication, I think it was about 0.28 millimeters gap. What you actually do is gap the core for the required inductance here, not for the actual air gap itself. When you're winding your own magnetics, you can either grind, if it's a small gap, you can grind out the center leg just with a small file. In this case here, I've cheated a bit because it's a small gap. I've just gapped all 3 legs, so put small bits of tape in just to give us the required inductance. In practice, in production, you'd always just gap the center leg, otherwise you get fringing fields and EMI problems. But for a first prototype, you can just do this approach whereby you gap all the 3 legs. We then wrap some tape around to hold everything in place. In production, you would normally the cores would be glued together. I haven't done that here. I've just used tape to hold it in place, and that's it. You can then go off and quantify and measure the parameters you've got for your part and just check that it all behaves itself. Okay, so I put this on an impedance bridge, and we've measured a primary magnetizing inductance of pretty close. I was quite pleased with this. Pretty close to 1 millihenry, 1.02 millihenries. Note the primary leakage inductance. You get that by shorting the secondary winding out and measuring the primary inductance. That's tiny here. It's 4 microhenries, and it's that low because we've used this interleaved approach. We can measure the turns ratio by looking at the ratio of the primary to secondary inductances, and we get about 2.8, so that's roughly what we wanted. This is an interesting part, the primary resistance. You can see if I measure the primary resistance at DC, we get 0.33 ohms. Now, if I measure that primary resistance at 100 kilohertz, it goes up to 2.2 ohms. Now, this is coming back to the effects I described back at the start of this webinar, the skin effect, proximity effect. Both of those act to increase resistance as you go up in frequency. So it's gone up by a factor of about 6 here at 100 kilohertz. And similarly, the secondary resistance at DC is about 70 milliohms, but at 100 kilohertz, it's about 340 milliohms. So again, similarly, the secondary resistance is increasing. Now, if we then use those 100 kilohertz frequencies based on the RMS currents we've got, we can work out the primary and secondary winding losses. And in this case, it's about 1.2 watts in total. So that's the winding loss estimates there. What about core loss? Well, we can use that. Remember those equations we developed before, the Steinmetz equations. If we've got in this case here, we have a triangular AC flux variation of about 260 milliteslas peak to peak at 100 kilohertz. And you can see here in this particular definition from the TDK data sheets, we have to use the RMS value of the magnetic flux density. So 260 milliteslas peak to peak at this duty cycle gives us about 75 milliteslas RMS at 100 kilohertz. Yeah, we get 30 kilowatts per meter cubed at 100 degrees C and 80 kilowatts per meter cubed at 25 degrees C. And the volume of the core, the EF30 core, or the 2 core halves together, is about, well, it's 4,000 millimeters cubed. And if you work out what that means, it means the core loss is approximately 120 milliwatts at 100 degrees C and 320 milliwatts at 25 degrees C. So you can add that on with the winding loss and gives a total transformer loss of around about 1.5 watts, worst case, ignoring the fringing effects for the moment. So that's quite useful. It gives you an idea on what sort of losses you're going to get in your transformer part here. You can also put this part then onto a frequency analyzer or an impedance analyzer, which measures the complex impedance as a function of frequency. So we've done that here. And you can see you get a self-resonant frequencies. All magnetic components will have a self-resonant frequency beyond which they behave more like a capacitor. This gives you an ability to measure the parasitic winding capacitance on our system. So in this case here, for the one we measured and the one we made and measured, the self-resonant frequency is about 1.2 megahertz, which is fine because we're only running at 100 kilohertz. That gives us a primary capacitance of about 17 picofarads, which again makes sense for the sort of size of component we've got here. And you can use that then in modeling if you want to as well, because that will contribute loss to your switching system. Let's look at flux density in the core for this particular example. So again, this is just the flyback converter we just built. If we model the primary with 1.07 amps flowing, you can see that the flux density in the core is not uniform. We've got, again, the fringing fields that we spoke about before near the air gap, but I think we're more than 3 times the air gap distance from those to the first layer of windings. So we're in a fairly good place with that design. Again, if we plot the flux density along that line, you can see we've got similar to what we had before, fairly well contained flux just in the ferrite with a little bit of fringing in the air gap region. Let's take a look at the winding current density. I've put this slide in just to show you what impact fringing, eddy current losses and proximity effect can have. If we just assume DC in those windings, the current density would be uniform. So that's a nice constant pink color wherever you are in the windings. And it's about 2 amps per millimeter squared. Yeah, that looks fine. However, we know we're not running DC, we're running 100 kilohertz. So with 100 kilohertz, things change a lot. And this is using the FEA tool. If you're interested in finite element modeling, we're going to spend an entire session next Tuesday talking about the details of how to use FEA techniques to model your magnetics components in a lot of depth. So do join us for that next Tuesday if you can. You can see here with 100 kilohertz, things change a lot. The winding resistance, well, actually, if I go back, where are we? Here, I think it is. It's not there. Yeah, okay, I'll whiz back through that in a minute. We'll go into that next week. You can see here that the winding resistance increases, and you can see here that you can see graphically that's happening here, because in the proximity or in the region of the air gap, you can see here there's far higher current density in the windings than there are if you're out at the periphery here. And also you can start to see, if you were to zoom in on this, the effect of proximity losses, whereby current flowing in the same winding is they're trying to flow in opposite sides of the conductors, and I'll show you that in a minute as well. If you imagine a vertical line now going down through that first layer of windings, and we plot the magnitude of the current density in those windings, you're going to have to turn your head on the side a little bit, because I've put this plot on the side to try and relate it to the physical aspects of the winding. You can see here that we have a very significant change in current density as we progress along that first layer of windings. And in the region of the air gap, we're getting up to some very high current densities at specific points in that windings, and then we head back to the sort of 3 to 5 amps per millimeter squared as we're out towards the periphery. So again, this is a benefit of the FEA approach that gives a fantastic oversight and understanding into the detailed behavior under high frequency. It's really worth getting into this stuff. If this is actually a zoom in, I think it's of some windings here in the periphery of the air gap, sort of buried in. You can see here we've got currents the current densities that are way higher at the edges, and that's just to do with the combination of all the different effects that we've got going on in this particular system here. The key thing is that the current density is far from uniform through the winding. It varies significantly, and all of it gets harder and harder as you go up in frequency. So we've just about come to the end of the webinar now. I thought it would overrun a little bit, so thanks for bearing with me on this. I'll just summarize the content I presented today, and then we'll move on to some questions. From my opinion, if you just start designing your own magnetics, it gives you control over all aspects of the performance trade-off for your application. Now, if you're pushing very high power levels, or you want to really push at the limits of performance, you really need to be getting into magnetics design to help you achieve that. Wide bandgap devices, if you're going to use those to their full capability, you need to make sure your magnetics is keeping pace. And it's very hard to communicate your design intent to a magnetics vendor and then get them to do this for you. because they don't understand your application in the way you do. So I'd really encourage you to get into some level of magnetics design if you're trying to push the limits, because that's how you're going to really get to the high performance levels that we see. There is some maths, and I hope it's not put too many of you off today. I've tried to keep it to a level where it just gives you an understanding of the interplay and how you can trade off different aspects of the design as you progress. There's a lot more to the mathematical modeling side that you can get into, but you don't need to go into that too much. You just need to understand the basic equations and how to use those to come up with your designs. The area product approach is a great starting point for sizing your magnetics. It's a starting point. There are other techniques for example, as you go up in size of your magnetics, so as you go to higher and higher power levels, the cooling of your transformer or your inductor becomes harder because you've got a lot more volume of material generating heat for a given surface area. So there are other approaches that tend to look at it from a more thermal perspective, but they're more complex to use. So one thing I would say is if you're going to bigger and bigger magnetics, you need to start backing off the winding current density and perhaps your ambitions on peak flux density to keep core loss manageable, or you need to look at ways of cooling those parts more effectively. I haven't really discussed parasitic effects today, we just haven't had time to do it. But as you start developing your own magnetics, you also start to get a feeling of what physically you're doing on the windings and the impact that might have on, say, for example, winding capacitance or leakage inductance, because all of those things have a bearing on how your converter performs. So by starting to wind and make your own magnetics, you start to understand how to maximize performance in terms of parasitics as well. The key thing here is when you get used to prototyping your own magnetics, you can prototype and de-risk and optimize your design so much faster than you can if you're dependent on an external vendor. You know, if a vendor takes 6 weeks to get a custom design back to you that's wrong, you've just lost 6 weeks on your project. The best thing you can do is do the early prototyping yourself, go through a few iterations, optimize it, and then start engaging with a magnetics vendor once you know that the magnetics part is roughly where you need it to be. Otherwise, your project schedules can go way out, and that just costs money. As I said before, we're going to go into some detail on finite element techniques next week. It's something we've started doing here on many designs now, and it's a fantastic way to really understand the details of how these magnetics components operate. So do join us next week where we'll go through that in a lot more detail. And I think that brings us nicely now to the end of the presentation. So thanks for bearing with me on that, and we'll take a look at some of the questions. Right, here we go. Okay, so the question at the top, here we go. What tool are you using for the magnetic flux density simulations? Okay, so again, this is the tool we'll talk about next week. It's actually freely available, which is brilliant. You know, it's most finite element packages are quite expensive and difficult to use. There's a freeware tool called FEM, F-E-M-M, and if you search for F-E-M-M online, you can download a free copy of that, and it's eye-opening what you can do with that. It's an absolutely fantastic tool, and I would strongly recommend just downloading it, playing with it, model a few bits and pieces, and you'll just see how useful it is to start getting into FEA modeling. I'll be showing you how to use it next week on the webinar, but yeah, if you can play around with it in advance of that, that's fantastic. So the next question down, what are the tests that should be done to confirm the functional properties before installing in circuits? So that's, I think, a generic question about your your inductive element or your magnetics elements. The key thing is to measure the parameters which are critical. So for example, if you're designing that flyback transformer like I described before, the key things that you need to make sure are correct is a primary inductance. That if you don't get that right, it's not going to behave itself. You need to have the turns ratio right. And then you probably want to measure things like leakage inductance and the AC and DC resistances. Once you've done that, then you're in a pretty good place. And in the flyback converter, the thing that most often goes wrong is people get the winding polarities wrong when you put it in the circuit, and you get some power throughput and then it doesn't really work. So you need to be careful on winding polarities. But generally, if you measure those main black box parameters that you've designed for, and they're within 5% of what you expect them to be, you're in a pretty good place. The next one down, how do you get the diameter for the primary winding? How did you get the diameter for the primary winding? I don't know whether that relates to the actual. I think what that question is asking is essentially, why did I choose a 0.45 millimeter wire?
That was on the example of the flyback.
Yeah, okay.
That was when they asked the question.
Sure. Okay. Perfect. Thanks, Jose. So in that case, the diameter of the primary winding. Let's take the case. Well, it's this wire here. It's the one I showed you. So we wanted, as part of our design approach, we wanted to run around about 3 amps per millimeter squared. And as part of the design exercise, which I didn't show you, if I go back, well, I think I won't show the slide here. From the transformer parameters that I showed you, we calculated that the primary RMS current worst case was 0.41 amps. So if you've got 3 amps per millimeter squared you need to support, and 0.41 amps RMS, you can work out based just on the what diameter you need to achieve that current density. So you choose the diameter based on the current density that you're trying to achieve and the current you're supporting. Next question down. Some cores have partial gaps which don't cut through the whole cross section. Is it just for saturation prevention? That's an interesting one. I remember seeing something like that quite a few years ago now. One thing about ferrite with an air gap is you have a very sharp saturation behavior. You've got a uniform air gap. If you run the core flux density up and up, suddenly the core will start to saturate and your inductance drops off a cliff. So if you plot inductance against current, it remains flat, flat, flat and goes down. When you start putting cuts into the core which don't go all the way across, what can actually happen is you can get partial saturation of certain regions. So you can actually start, I think this is what you're indicating anyway, you can start causing a much softer saturation because it doesn't all saturate at once. You can control the saturation behavior. There was a good example, I remember years ago working on a very high power audio amplifier for a car, which had a transformer which was formed from 2 toroids, one inside the other, and they were different materials. And I think the idea there is that if there was a saturation problem on one of them, you didn't lose everything. You still had some reluctance in there. So it's a way to control saturation normally, or at least the sharpness of the saturation. Next question up, is a database available that provides core area product for common core shapes? Together with the thermal, I think RTH being thermal impedance. I'm not aware of that, actually. That would be an interesting thing to have. What I've done is that spreadsheet I showed you where I literally go around and I find all that information from the data, at least the core area and the product of the core area and the winding area, and I've made my own spreadsheet up for common cores that we use here, and that tends to be enough. I've not seen anything that specifically goes into RTH thermal impedance, so I've not seen anything there. There's $1 million question here. In practice, what would be the max frequency that we can design a transformer for? There's no real way to answer that. It really depends. Designing the transformer, if you want to go higher and higher in frequency, ultimately what you're going to end up doing is having a thermal problem. So if you really want to run at high frequency, you have to manage the thermal situation better, is one way to deal with that. Or as you go up in frequency, you have to start backing off the flux density you're running at to manage the core loss. So it ends up being a thermally limiting situation. So if you can't cool a transformer well enough, you have to back off the delta B. And if you back off the delta B, it means that to go up in frequency, you're actually starting to make the transformer bigger again. So you're losing the benefit. For very high frequency systems, you can, well, this is why with wireless charging, people run at very high frequencies because there's no core there to worry about. Typically, the operating frequencies we're running might be a few hundred kilohertz at most for isolated approaches. If you've got board level DC to DC converters, you can get those running reasonably well at a few megahertz, something like that. So it really depends on your application.
There is an interesting question if you scroll down about a multi-port transformer.
Oh, yes. Okay.
And people have voted that as interesting question as well. So.
Oh, cool. Okay. Yeah, actually, that's a very good question. We actually looked at a multi-port topology. I'm trying to think what the topology we use. But a multi-port essentially is the transformer becomes a component which couples in different energy sources, or at least that's how we were treating it. So, for example, if you've got a micro generation scheme where you want to have solar input, or you might want to have mains power input or battery storage, all of these things, you can find that the transformer, if you design it correctly, can be something which allows you to couple the energy between all of these different systems and manage the energy flow. In that case, it's interesting. I think the sort of things that you tend to run, or the problems you tend to run in, it depends on the topology really, but if you're running high power levels, you want to make sure that the highest power path has windings which are the most tightly coupled, because leakage inductance can often cause you problems. If they're not well coupled, then you start to have problems there. So if I was designing a transformer for a multi-port system, I would look at the systems which are trying to couple the most power level, and I would prioritize the windings in that transformer so that they're very close to one another, so we get low leakage. It's a bit like, for example, in that mains flyback I showed you earlier. I showed one output which is 48 volts. You can have other auxiliary outputs, but if they're just providing a few hundred milliwatts, well, you want to make sure that the primary and the main 48 volt winding are well coupled, and then you sacrifice the coupling to the lower power windings because they don't really influence behavior that much. So it's really probably power that would dictate the winding structure there. Let's have a look. I'm sure we've got a few more here.
There's one below about the core grade. What is core grade?
What is the core?
Basic question.
Okay. Yeah, so I think by that you mean...
It was at the beginning of the webinar.
Oh, okay. So that's the... Okay. So the core grade, what I mean by that is the type of ferrite or the type of iron powder material. So I think I showed a table at the start whereby we had different grades of ferrite material. So the ones I showed were from TDK, and there were about 5 or 6 different types. And their terminology is N97, N98, N96. So the different grades of ferrite, in that case, play or allow you to play around with core loss versus peak saturation flux density, or maybe the operating temperature range. They have a different mix for the ferrite that allows you to choose the behavior that you most need in your application, whether it's low loss or high temperature or whatever it is. It's the parameter behavior of the ferrite gives different grade types. There's a question just come in at the top.
There are 3
what are the approach
questions left.
Oh, okay. I'll try my best to go through them. If people want to hang on, I'll do my best to go through them. So what are the approaches?
They are quite short.
Okay, what are the approaches to take to increase the leakage inductance? That's a great question. So, for example, in an LLC converter, a resonant converter, actually the leakage inductance is a target design parameter. And actually you want to put leakage in there. So the flyback I showed you here, we try to minimize the leakage, and we did a good job on that. If you want to have an LLC converter with whereby you're utilizing the leakage inductance of the series resonant inductor, you normally need a leakage inductance which might be, I don't know, ratios, probably 10 to 20% of your magnetizing inductance might be a particular design metric. It's quite hard to design it. I guess you could use FEA approaches to look at leakage inductance. Maybe we look at that next week on the call. But basically, if you want to increase the leakage inductance, all you can do is realistically is space the windings apart. It's not really there's no real rocket science to that. The difficult part is knowing how far to space them apart to get the inductance you want. We do that empirically. So we've done that for LLC converters at up to about 2 kilowatts on a single platform. You have to be a little bit careful increasing leakage inductance too much using that technique, because remember, leakage inductance is essentially magnetic flux, which is generated by one winding which isn't coupled to another. So leakage inductance in that context is stray fields in the air. So it can create a lot of EMI if you're not, or heating in other nearby parts of the circuit. So be careful for high power systems using leakage inductance as a real element. You might be best off using a separate physical discrete inductor for the LLC case anyway.
There are 2 questions left.
Okay, I'll finish off these 2. So
one about the slides availability.
Yeah, so the slides, no, as you saw on the presentation today, these slides have a lot of animations to try and help communicate what we're doing, and that don't come out well in if we just create a PDF from them. However, the best thing to do, we're putting these, all of these videos are recorded and they're on our website, so you'll be able to access these on demand on our website afterwards. Yeah, let us know if you want the link for that. This one will go up today, so you can review the content again then. And I think we've just got one more.
Yeah.
Down at the bottom.
That's about high frequency transformers.
Okay, I'll just find that one. Oh, here we go. Is it possible to take the design approach from today's webinar to design transformers for very high frequency? Yeah, you can. As you get up to those frequency levels, obviously core loss and all the loss mechanisms that I described to you today become particularly acute, and you've got to be very, very careful to minimize those. So in theory, yes, you can use those approaches, but you've got to be careful, certainly with the skin depth approach, proximity losses, all that sort of stuff, core losses, you have to use very low flux densities. The other thing to be careful of is if you're operating at high frequency, a high frequency transformer at 1 megahertz or thereabouts, the parasitics that I've spoken to you about start to become a problem. So remember that flyback transformer I showed you? That had a self-resonant frequency of only 1.2 megahertz. Now you wouldn't want to run anywhere close to that 1.2 megahertz operating frequency for that flyback. It just would not behave well. So if you do want to run at those really high frequencies, you need to use techniques to significantly reduce parasitic capacitance. So winding structures become very important, and loss. So hopefully that's, I think
there is one last, or no, that's the chat.
Yeah, I think that's covered everything. I hope this has been a useful webinar for everybody today. It's I'm actually fascinated by magnetics. It's such an interesting area of power electronics because there is a real interplay with the real power converter. And I do hope it's been presented in a way which has been accessible for you today. If it has been, please do sign up to join us next week for the finite element webinar, where we'll go into some real details of how to use that FEMM tool to show you how to design various different components. But thank you very much for joining today, and I hope to see you soon. Thank you.